The reason circuits for electrical cranes operating over combustible fibers in Class Roman III locations are specifically required to not be grounded, while grounding is not prohibited in Class I and Class Roman II locations, is due to the unique characteristics of Class Roman V environments. Class Roman III locations are defined as areas where easily ignitable fibers or materials producing combustible flames are handled, manufactured, or used. These materials are typically non-conductive, meaning they do not readily conduct electricity. However, when these materials are suspended in the air as dust or fibers, they can create a hazardous environment if an electrical spark or arc occurs. In a grounded system, any fault or accidental contact between the electrical circuit and the ground can create a path for electrical current to flow. This can result in the generation of sparks or arcs, which can ignite the combustible fibers in Class Roman III locations. Therefore, to minimize the risk of ignition, circuits in these areas are required to be ungrounded. In contrast, Class I and Class Roman II locations are defined as areas where flammable gases, vapors, or liquids are present. These materials are typically conductive, meaning they can conduct electricity. In these locations, grounding is generally required to provide a safe path for electrical current to flow in the event of a fault or accidental contact. Grounding helps to limit the voltage that can accumulate in the circuit and reduces the risk of electrical shock or fire. It's important to note that the specific grounding requirements for electrical circuits in hazardous locations are determined by the National Electrical Code, or NEC, and other applicable codes and standards. It is crucial to follow these requirements carefully to ensure the safety of personnel and property in these potentially hazardous environments. To further elaborate on the differences and rationales behind the grounding requirements in Class I, Class Roman II, and Class Roman III locations, let's delve into each classification in more detail. This will provide a clearer understanding of why certain measures are taken in each environment to mitigate the risk of fire and explosion. Firstly, let's discuss Class I locations. These are areas where flammable gases or vapors are or may be present in the air in quantities sufficient to produce explosive or ignitable mixtures. Examples of Class I locations include petroleum refineries, gasoline storage areas, and locations where volatile solvents are used. In these environments, the primary hazard is the presence of flammable gases or vapors that can easily ignite if exposed to a source of ignition, such as an electrical spark or hot surface. Grounding is essential in Class I locations to minimize the risk of electrical shock and to provide a low impedance path for fault current to flow back to the source. This helps to quickly trip over current protection devices, such as circuit breakers or fuses, and to energize the circuit in the event of a ground fault. By quickly clearing ground faults, grounding reduces the likelihood of sparks or arcs that could ignite the flammable atmosphere. Furthermore, grounding helps to equalize the potential between different conductive objects in the area, reducing the risk of static electricity buildup and discharge, which could also serve as an ignition source. Secondly, we move to Class Roman II locations. These are areas where combustible dust is present in the air in quantities sufficient to produce explosive or ignitable mixtures. Examples of Class Roman II locations include grain elevators, flour mills, coal preparation plants, and areas where metal dusts are generated. In these environments, the primary hazard is the presence of combustible dust that can explode or ignite if suspended in the air and exposed to a source of ignition. Grounding is also important in Class Roman II locations, but the focus is slightly different compared to Class I locations. In Class Roman II locations, grounding helps to prevent the buildup of static electricity on equipment and machinery, which could discharge and ignite the combustible dust cloud. Grounding also provides a path for fault current to flow in the event of a ground fault, helping to trip over current protection devices and to energize the circuit. However, special attention must be paid to the design and installation of electrical equipment in Class Roman II locations to prevent the accumulation of dust on surfaces and to ensure that the equipment is rated for use in dust ignition-proof environments. Dust ignition-proof equipment is designed to prevent the ingress of dust and to contain any sparks or arcs that may occur within the enclosure, preventing them from igniting the surrounding dust cloud. Finally, let's consider class Roman 3 locations. As previously mentioned, these are areas where easily ignitable fibers or materials producing combustible flames are handled, manufactured, or used. Examples of class Roman 3 locations include textile mills, woodworking plants, and areas where paper or cotton is processed. In these environments, the primary hazard is the presence of easily ignitable fibers or flames that can quickly catch fire if exposed to a source of ignition. Unlike Class I and Class Roman 2 locations, the materials in Class Roman 3 locations are typically non-conductive. This means that grounding is not as effective in preventing the buildup of static electricity or providing a low impedance path for fault current to flow. In fact, grounding can actually increase the risk of ignition in Class Roman 3 locations. If a grounded circuit comes into contact with a combustible fiber or flame, it can create a path for electrical current to flow through the material to ground. This can generate heat and sparks, which can easily ignite the combustible material. For this reason, the NEC requires that circuits in Class Roman 3 locations be ungrounded to minimize the risk of ignition. Ungrounded circuits are designed to prevent the flow of fault current to ground, reducing the likelihood of sparks or arcs that could ignite the combustible fibers or flames. Instead of relying on grounding for fault protection, ungrounded circuits typically use ground fault detectors to monitor the insulation resistance of the circuit. If a ground fault is detected, the ground fault detector will alarm or trip the circuit breaker, alerting personnel to the problem and allowing them to take corrective action before a fire can occur. In summary, the grounding requirements for electrical circuits in hazardous locations are based on the specific hazards present in each type of environment. Grounding is generally required in Class I and Class Roman 2 locations to minimize the risk of electrical shock, prevent the buildup of static electricity, and provide a path for fault current to flow. However, in Class Roman 3 locations, grounding is prohibited to minimize the risk of ignition of combustible fibers or flames. It is crucial to carefully follow the NEC and other applicable codes and standards when designing and installing electrical systems in hazardous locations to ensure the safety of personnel and property. The NEC provides detailed requirements for the selection, installation, and maintenance of electrical equipment in hazardous locations, including requirements for grounding, bonding, wiring methods, and equipment enclosures. These requirements are designed to minimize the risk of fire and explosion and to protect personnel from electrical shock. In addition to the NEC, other organizations such as the National Fire Protection Association, or NFPA, and the Institute of Electrical and Electronics Engineers, or IEE, also publish standards and recommended practices for electrical safety in hazardous locations. These standards provide valuable guidance on how to design, install, and maintain electrical systems in these challenging environments. It is important to note that the requirements for electrical systems in hazardous locations can vary depending on the specific application and the type of hazardous material present. Therefore, it is essential to consult with a qualified electrical engineer or other expert to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. Furthermore, it is important to conduct regular inspections and maintenance of electrical equipment in hazardous locations to ensure that it is in good working order and that it meets all applicable safety requirements. This includes inspecting equipment enclosures for damage, testing grounding connections, and verifying the proper operation of overcurrent protection devices and ground fault detectors. By following these best practices, it is possible to minimize the risk of fire and explosion in hazardous locations and to protect personnel from electrical shock. The specific requirements for grounding and bonding in hazardous locations are outlined in Article 250.100 to 250.108 of the NEC. These sections provide detailed guidance on how to properly ground and bond electrical systems in Class I, Class Roman 2, and Class Roman 3 locations. For example, Section 250.104 of the NEC requires that all metal raceways, cable trays, and other metal enclosures containing electrical conductors be bonded together and connected to a grounding electrode system. This helps to create a low impedance path for fault current to flow and to minimize the risk of electrical shock. Section 250.1 106 of the NEC provides specific requirements for grounding electrode systems in hazardous locations. It requires that the grounding electrode system be designed to provide a low impedance path for fault current to flow and to minimize the risk of electrical shock. The grounding electrode system must also be designed to withstand the effects of corrosion and other environmental factors. In addition to the grounding requirements, the NEC also provides specific requirements for bonding in hazardous locations. Bonding is the process of connecting together all metal parts of an electrical system to create a low impedance path for fault current to flow. Section 250.102 of the NEC requires that all metal parts of an electrical system in a hazardous location be bonded together using bonding jumpers or other approved methods. The bonding jumpers must be sized in accordance with the requirements of the NEC and must be installed in a manner that ensures a reliable electrical connection. The NEC also provides specific requirements for the selection and installation of electrical equipment in hazardous locations. Article 500 of the NEC provides general requirements for electrical equipment in hazardous locations, while Articles 501, 502, and 503 provide specific requirements for Class I, Class Roman II, and Class Roman III locations, respectively. These articles cover topics such as the type of equipment that is permitted to be used in each type of hazardous location, the wiring methods that are permitted to be used, and the requirements for equipment enclosures. The NEC also provides specific requirements for the installation of electrical equipment in hazardous locations. These requirements are designed to minimize the risk of fire and explosion and to protect personnel from electrical shock. For example, the NEC requires that all electrical equipment in a hazardous location be installed in accordance with the manufacturer's instructions and that it be properly supported and secured. The NEC also requires that all electrical equipment in a hazardous location be inspected and tested on a regular basis to ensure that it is in good working order and that it meets all applicable safety requirements. In addition to the NEC, other codes and standards may also apply to electrical systems in hazardous locations. For example, the NFPA publishes a number of standards that provide guidance on electrical safety in hazardous locations, including NFPA 70E, Standard for Electrical Safety in the Workplace, and NFPA 496, Standard for Purged and Pressurized Enclosures for Electrical Equipment. These standards provide valuable information on how to protect workers from electrical hazards and how to properly design and install electrical systems in hazardous locations. In conclusion, understanding the differences between Class I, Class Roman II, and Class Roman III hazardous locations and the specific grounding requirements for each type of environment is crucial for ensuring electrical safety. By following the NEC and other applicable codes and standards, it is possible to minimize the risk of fire and explosion and to protect personnel from electrical shock. Always consult with a qualified electrical engineer or other expert to ensure that the electrical system is designed and installed in accordance with all applicable requirements. The differences in grounding practices stem from the fundamental nature of the hazards in each class. Class I hazards involve flammable gases or vapors which, when mixed with air in the right proportions, create an explosive atmosphere. The concern here is that even a small spark can trigger a devastating explosion. Grounding in Class I locations is vital for safety because it helps to quickly clear electrical faults. When a fault occurs in a grounded system, the fault current has a low resistance path back to the source. This high current causes overcurrent protection devices, like circuit breakers or fuses, to trip rapidly, cutting off the power to the faulty circuit. This rapid de-energization minimizes the duration of any potential arcing or sparking, greatly reducing the risk of ignition. Furthermore, grounding helps to equalize the electrical potential between different conductive objects in the hazardous area. This prevents the buildup of static electricity, which can also discharge as a spark and ignite the flammable atmosphere. In Class Roman II locations, the primary hazard is combustible dust. This dust can be easily ignited by a spark or hot surface, leading to a flash fire or even a dust explosion. While grounding is still important in Class Roman II locations, the emphasis shifts slightly. The main goal is to prevent the accumulation of static electricity on equipment and machinery. As dust particles move around and rub against surfaces, they can generate static charges. If these charges build up sufficiently, they can discharge as a spark, potentially igniting the surrounding dust cloud. Grounding provides a path for these static charges to dissipate safely, preventing them from reaching dangerous levels. Additionally, grounding in Class 1 and 2 locations provides the same fault-clearing benefits as in Class I locations. If a ground fault occurs, the fault current will trip over current protection devices, minimizing the risk of ignition. However, it's crucial to use dust ignition-proof equipment in Class 1 and 2 locations. This equipment is designed to prevent dust from entering the enclosure and to contain any sparks or arcs that may occur within, preventing them from igniting the surrounding dust cloud. Class 1 and 3 locations present a different set of challenges. Here, the hazard is easily ignitable fibers or flyings, such as those found in textile mills or woodworking plants. Unlike the flammable gases and conductive dust of Class I and Class 1 and 2 locations, these fibers are typically non-conductive. This means that grounding is not as effective in preventing the buildup of static electricity or providing a low impedance path for fault current. In fact, grounding can actually increase the risk of ignition in Class 1 and 3 locations. Consider a scenario where a grounded circuit comes into contact with a pile of combustible fibers. The fibers, being non-conductive, won't provide a good path for current to flow. However, if there's enough moisture or contamination present, a small amount of current might still flow through the fibers to ground. This current flow can generate heat and sparks, which can easily ignite the fibers. By requiring circuits in Class 1 and 3 locations to be ungrounded, the NEC eliminates this potential ignition source. Ungrounded systems are designed so that a single ground fault will not cause the overcurrent protection devices to trip. Instead, a ground fault detector is used to monitor the insulation resistance of the circuit. If a ground fault is detected, the detector will alarm, alerting personnel to the problem. This allows them to locate and repair the fault before it can cause a fire. It's important to note that ungrounded systems are not without their drawbacks. They can be more difficult to troubleshoot than grounded systems, and a second ground fault on a different phase can create a short circuit and trip the overcurrent protection devices. However, in Class 1 and 3 locations, the benefits of preventing ignition outweigh these disadvantages. In summary, the grounding requirements for hazardous locations are carefully tailored to the specific hazards present in each class. Grounding is essential in Class I and Class 1 and 2 locations to quickly clear faults, prevent static electricity buildup, and minimize the risk of ignition. However, in Class 1 and 3 locations, grounding is prohibited to prevent the flow of current through combustible fibers, which could lead to ignition. Understanding these differences is crucial for ensuring electrical safety in hazardous locations. Always consult the NEC and other applicable codes and standards to ensure that electrical systems are designed and installed in accordance with all requirements. Also, remember that proper training and maintenance are essential for maintaining electrical safety in hazardous locations. Workers should be trained to recognize the hazards present in their work environment and to follow safe work practices. Electrical equipment should be inspected and tested regularly to ensure that it is in good working order and that it meets all applicable safety requirements. By taking these precautions, it is possible to minimize the risk of fire, explosion, and electrical shock in hazardous locations.